Life is a fascinating journey, full of unknowns. Every day, we face situations where outcomes aren't guaranteed, from predicting tomorrow's weather to wondering if your favorite team will win. How do we make sense of this inherent uncertainty? How do we quantify it, and more importantly, how do we make smart decisions when we don't know exactly what will happen next? That's precisely where probability comes in, offering us a powerful lens through which to view and navigate the world of chance. At its core, probability is simply the measure of how likely an event is to occur. It's a numerical value, always falling between 0 and 1. A probability of 0 means an event is impossible. It will never happen. A probability of 1 means an event is certain. It will definitely happen. Everything in between represents varying degrees of likelihood, giving us a common language to discuss possibilities. Let's think about some everyday examples. If you flip a fair coin, what's the probability it lands on heads? There are two equally likely outcomes, heads or tails. So, the probability of getting heads is 1 out of 2, or 0.5. Similarly, if you roll a standard 6-sided die, the probability of rolling a specific number, say a 4, is 1 out of 6, approximately 0.167. These simple scenarios highlight how we can assign numerical values to uncertainty. To truly understand probability, we need a few key terms. An experiment is any process that produces an observable result. Flipping a coin or rolling a die are experiments. An outcome is a single result of an experiment, for example, getting heads on a coin flip, or rolling a 3 on a die. An event is a collection of one or more outcomes. So, rolling an even number on a die is an event. The sample space is another fundamental concept. It's the complete set of all possible outcomes for a given experiment. For a single coin flip, the sample space is heads, tails. When rolling a 6-sided die, the sample space is 1, 2, 3, 4, 5, 6. Defining the sample space is crucial because it gives us the full picture of what can happen, allowing us to accurately calculate probabilities. Calculating simple probabilities follows a straightforward formula. The probability of an event is the number of favorable outcomes divided by the total number of possible outcomes in the sample space. So, for our coin, the number of favorable outcomes for heads is 1, and the total possible outcomes are 2, giving us 1/2. For rolling a 4 on a die, it's 1 favorable outcome out of 6 total, or 1/6. Sometimes, it's easier to think about what happened. This is where the complement rule comes in handy. The probability of an event happening is simply 1 minus the probability that it happened. For example, if the probability of rolling a 6 is 1/6, then the probability of rolling a 6 is 1/1/6, which equals 5/6. This rule is incredibly useful for simplifying calculations. Events can relate to each other in different ways. Mutually exclusive events are those that cannot happen at the same time. If you roll a single die, you cannot roll both a 1 and a 2 simultaneously. They are mutually exclusive. For mutually exclusive events, the probability of A, B occurring is simply the sum of their individual probabilities P equals P plus P. On the other hand, non-mutually exclusive events happen at the same time. Imagine drawing a single card from a deck. The event of drawing a red card and the event of drawing a face card are not mutually exclusive, because you can draw a red face card. When events are not mutually exclusive, the probability of AB is P plus PP, where we subtract the overlap to avoid double counting. Now let's consider how the occurrence of one event affects another. Independent events are those where the outcome of one has absolutely no impact on the outcome of the other. For instance, if you flip a coin twice, the result of the first flip does not change the probability of the second flip. For independent events, the probability of AB both occurring is the product of their individual probabilities P equals P asterisk P. In contrast, dependent events are linked. The outcome of one event changes the probability of another. Drawing 2 cards from a deck is a classic example. The probability of drawing a second specific card changes once the first card has been removed. This leads us into the concept of conditional probability, which calculates the probability of an event given that another event has already occurred. Probability isn't just a theoretical concept for textbooks, it's a cornerstone of real-world decision-making. Businesses use it to assess risk, forecast sales, and develop new products. Insurance companies rely heavily on probability to calculate premiums. Individuals use it intuitively when checking a weather forecast to decide whether to carry an umbrella, or when considering the odds of winning a lottery. The law of large numbers provides a fascinating insight into probability. It states that as you repeat an experiment many times, the observed frequency of an event will eventually converge on its theoretical probability. So, while a few coin flips might not give you exactly 50% heads, flip it thousands of times, and the proportion of heads will get incredibly close to half. This principle is vital for statistical reliability. Understanding probability is more than just knowing formulas. It's about developing an intuitive grasp of uncertainty. It forms the bedrock of statistical inference, allowing us to draw conclusions about larger populations based on smaller samples, even when we don't have perfect information. By quantifying uncertainty, probability empowers us to make more informed, rational decisions, navigate complex situations, and unlock deeper insights into the world around us.